set of lectures on beginning descriptive statistics, I'm going to talk about your measures of variability. So this is, again, a summary statistic, but it tells you something quite distinct from a central tendency statistic. Okay, so whereas the mean, or any of your central tendency scores, is meant to tell you something about where most of the scores in your distribution lie, another key piece of information in fully communicating and describing your data is whether or not the other scores in the distribution fall near or far away from the mean. In order to capture this, you will typically want to pair your mean or other average together with what we call a measure of variability. So a variability score is meant to be a value that tells you about just how much all of the scores in your distribution are spread out from one another. Are they clustered very close to the mean, or are they far flung? Are there scores that are very extremely far away from the mean? You tend to see a central tendency statistic paired together with a variability statistic because the two together give you a pretty fully fleshed out idea of what's going on with your data, at least when you're describing a single variable. So this is typically done because distributions of scores with the same mean can have very, very different extents of variability. So as you can see from these three different sets of scores, you can see that any data set that has a mean of 10 can be vastly different from one another, right? It could be that all of the scores are the same. So there's no variability in that top score, in that top set of scores. That bottom set of scores, again, mean of 10, but it's much, much more spread out. The middle one, it's kind of somewhere in the middle. What you want is to not only figure out where most of the scores lie, typically through the mean, you also want to describe your distribution a bit more fully by pairing it together with a variability statistic. So the most basic and the least informative way to do this is to just calculate the range. This is the simplest way to get variability. It's just the highest score minus the lowest score. So in this particular set of scores, you just subtract that 4 from the 31, range of 27. It gives you a really basic sense of the variability of your scores. It's not particularly informative, though, because you do throw out a ton of information. The range is just derived from the most extreme scores, the lowest and the highest score. So you do throw out a fair amount of information. So for example, you have these two very distinct data sets that have the same mean and the same range, right? That bottom one has a set of scores clustered lower towards the bottom with a big jump. The top data set, you see that 3 is kind of rogue, and then once you get up to 17, you see a pretty smooth spread of scores up to 36. So just using the range along with the mean would indicate that these two data sets are the same when in fact they're quite different. So here we bring in the variance and the standard deviation. These are your more useful variability measures. So standard deviation, if you are thinking back to in the last video where I harped on about deviations, it's about to become a lot more relevant here. So, as I defined earlier, a deviation is the amount by which a score differs from the mean. So we want to measure variability, so the idea is, can't we use deviation scores to figure out the average amount of variability? Well, yes, and this is what we call the standard deviation. And the standard deviation is definitely your most useful and your most widely used variability summary statistic. You might be thinking to yourself, I know where this is going. I'm just going to have to take an average of the deviation scores. Easy as that, right? Wouldn't that get you a good solid idea of the variability? Not quite. Consider that point I belabored into the grave just a few minutes ago in terms of how we defined the mean. I just mentioned that inherently it is true about the mean that the sum of the deviations around the mean will add up to 0, because again, the numerical weight of the values above the mean is equal to the numerical weight of the scores below the mean. So we have a problem. If we were to just take the mean of the deviations, think about why this doesn't work. You take the mean by taking the sum of scores and divide by n. If we were to just take the mean of the deviations, that value would always be 0 because the sum of the deviations is always 0. But the variability of scores is only 0 when all of the scores are the same. So this clearly does not work. We clearly cannot have a standard deviation calculation that would yield it always being 0, because that's just not true or accurate about the variability in our data sets. So there's a pretty simple equation that gets around this problem. If the problem is that the sum of the deviations always equals 0, and as such the average deviation will always be 0, there's a pretty easy solution. Since some of the deviation scores are negative and some are positive, you can square all of them and you can get rid of that problem. Okay, so it's as easy as this. You have your scores, you have your deviations. Okay, you can't use the sum of the deviations to calculate a standard deviation, and I swear to God, there will always be a student who does this and they get that standard deviation is 0 and it's the wrong answer. Do not do this. Okay, do not take that 0 right here and use that to calculate your standard deviation. You're going to want to square all of your deviation values. Okay, so this is a very, very important step. You're going to take the deviations of all your scores, and then you're going to square each and every one of those deviations for every single data point. Okay, this gets rid of the problem of the sum of the deviations being 0, because now that there's no more negative values, that sum of the squared deviations is only going to be 0 when there was no variability in the data set. So this is something we can actually use. So this is very exciting. This is a term that we refer to as the sum of squares. This is what helps us get around the theoretical issue whereby the sum of the deviations around the mean will be 0. We're going to take the sum of squares, which is the sum of all those squared deviations, and we're going to use that to calculate our standard deviation. Okay, so the sum of squared value, we're going to use that to calculate what we call our sample variance. So variance is going to be one of our variability measures that tells you a little bit about how spread out your scores are. So the variance and the mean together can help determine the overall shape of your distribution. The notation for variance is going to be s squared. There's also a population notation of your sigma squared. Again, you're not going to see that a ton because you're not often going to be calculating variance for a population, but you're definitely going to be seeing s squared. You might be asking yourself, why is it s squared? I'm going to have an answer for you. Okay? But before we get to that, again, the basic idea is that we're going to want to pair a central tendency statistic with a variability statistic, because those two things together are going to give us a good solid idea of what our distribution of scores looks like. So looking at this visual, that bell curve A versus that bell curve B, you can very easily see that it has the same mean, but the shape of those bells are very, very different, right? That B bell with its very, very low and wide spread indicates that there's a ton of variability. That data distribution A, on the other hand, has the same mean, but would indicate scores that are much more closely clustered together. These two competing sets of distributions, though, would describe two competing sets of data that had different means. They were oriented around different means, but the shape of that bell is exactly the same, indicating that the variability for those two curves was exactly the same. So that's why we want to pair a mean together with a variability statistic. All right, so here's your first equation. I wish I could see the looks on your faces, just sort of blank concern, but here we go. This is your formula for calculating variance. Again, the notation for variance is s squared. Again, this is your first more complicated equation of the semester. You might be thinking, what the fuck is that? That's fair. I'm here to tell you that basically if you followed along with my theoretical description so far, you know exactly what this is, and you should be able to use your knowledge of notation and order of operations to be able to use this equation no problem. Okay, so if you look at this equation and you break it down, you have all of the steps for calculating variance, and you don't need to memorize anything. You just need to know what to look for. So if you're looking at this and thinking to yourself, what do I do first? Well, notice that x minus x bar is in parentheses. You know you need to do that first. What that is directing you to do first before anything else is to get all of the deviations for all of your scores. Every single data point in your data set, you need to get the deviation. Parentheses comes first, next comes exponents. Okay, so you see that sigma, you see that exponent, you're thinking what do I do first? Exponent. So you get all the deviations done, and then you square all of the deviations. Only at that point will you then sum up all the squared deviations. Again, I cannot tell you how often it is that students will calculate all the deviations, sum up all the deviations, get 0, and then square the 0 to no avail, and think, I guess the standard deviation is 0. It's not, okay? Looking at this equation, deviations first, square the deviations, sum up all the deviations, okay? And that's just your numerator. Your denominator is super simple. It's just n minus 1, the sample size minus 1. You might be asking why n minus 1? Well, you can take that for granted, just knowing that you're going to have this equation on the exam and decide not to care. But for those of you who are interested, this is a concept that we call degrees of freedom, and you see it very often in the kind of statistics we do. Things will be evaluated based not on sample size, but like sample size minus 1 or minus 2 if you're talking correlations. The basic idea is that using degrees of freedom instead of sample size creates a slightly more conservative or smaller estimate of the variance. The idea being that most sample statistics are meant to approximate population parameters. And so using those slightly diminished estimates based on the degrees of freedom creates a bit more conservatism to try and avoid overestimating values that we then infer apply to the population. You might be thinking that sounds like garbage. Yeah, you might be right. It was Sir Ronald Fisher that came up with it, and he was like a famous racist. So again, if you decide that this is sufficiently boring and you never want to think about it again, that's absolutely fine. But if you were curious why it's n minus 1, it's because of this degrees of freedom concept that we will see throughout the semester. All right, so we're getting closer and closer to standard deviation. So we covered variance. Don't be too concerned that this is a completely different analysis. Variance and standard deviation are basically two different steps of the same calculation. So don't worry that I'm about to entirely shift gears and show you something entirely different. Standard deviation and variance are numerically and conceptually related to one another. Okay, so variance is an important statistic in many inferential statistical analyses. There's even a really important analysis called analysis of variance that is all about interpreting variance among different groups. So for other further more advanced analyses, you do see variance being a little bit more important. But in terms of its usefulness as a descriptive statistic for a single variable, it's a little bit trickier to interpret. The variance yields a variability statistic that's sort of out of scale or out of step with all of the actual values that appeared in your data set. That squaring that you did to get rid of the problem of the sum of the deviations being 0 yielded much higher scores than actually appeared in your data set. So the variance in and of itself, if you just look at the variance and look at your data set, it's sort of out of scale. It's just larger than it has to be. So the easy last step to get your standard deviation is just square root your variance to get rid of that quote-unquote out-of-scale problem. So like I said, standard deviation and variance aren't two different things. It's just once you get the variance, you got to do your last step of taking the square root to get your standard deviation. So this is your formula for standard deviation. It's the exact same as the one for variance, it's just the square root of it. This is why the notation for variance is s squared. It's because the notation for standard deviation is s. And since the variance is the standard deviation squared, variance, the notation is s squared. But the notation for standard deviation is just s. So this is your formula for standard deviation. Again, I walked through what you would do to get your variance, which is essentially the second to last step before you take that square root and get your ultimate standard deviation. Okay, so you get all the deviations, you square them, then you sum them, divide by degrees of freedom, square root. Okay, it's not as hard as it looks. Again, the idea is if you can remember your notation and the order of operations, equations are there to help you. They're the roadmap that tells you the steps you have to do. You shouldn't need to memorize this formula, you shouldn't need to memorize the steps. This is meant to be a guide as long as you can read and understand it. Okay, so if you just remember what these notations mean in the order of operations, this should be all you need to calculate yourself a standard deviation. Okay, so I'm going to quickly show an example of walking through how you would do this. So let's say I have a data set containing 10 scores. Here's how I would recommend walking through your calculation for the standard deviation. This is going to be a structure of how to set up your calculations that I'm going to recommend throughout the semester. It's basically to set up a series of columns for yourself where you do all of the steps in order. So first you want to create a column with all of your scores in the data set. To do a standard deviation, you definitely need to get the mean, so you can bang that out first, no problem. From there, you want to create a deviation column, so x minus x bar, all of the individual scores minus the mean. You have to do this for every single score. Okay, notice that I did the deviation for all 10 of the scores in my data set. Okay, so those are my deviations. Square them. Do not neglect to square them. Recall that if you add up this column, it will be 0 and it will be useless. Square the deviations in this last column and then sum them up thusly. Okay, so this value, your sum of squares, you're going to use that to calculate your variance and standard deviation. So you do variance first. You take that sum of squares and you just divide by the degrees of freedom. Your variance for this particular set of scores is 9.83. Your standard deviation, you just need to take that variance and take the square root of it. So your standard deviation, 3.14. If I was to ask in an exam for you to calculate the variance and the standard deviation, keep in mind that you don't need to do two separate calculations. Literally, the variance is just the second to last value that you're going to have in this calculation before you take the square root. Okay, so you don't need to do two separate calculations. Variance and standard deviation will both be computed along the process of computing standard deviation. Okay, so these would be your answers to your calculations. I'm going to show you an example of a publication that I have that used mean and standard deviation together to describe some data. And that's going to seg us into the discussion prompts that you have for your central tendency and variability statistics. So this is a publication of mine where I just did a really simple correlational study where I asked people a series of questions along two distinct scales. And as you'll see, for each of the scales, there's some basic descriptive information that was included. And this is going to mirror what you guys are going to ultimately do when you write up the results from your presentation. So you write up some description of the scale that you use. You can have a sample item. You want to indicate the response format, and then you indicate if you took an average. You would likely do an internal reliability. You can see I have a Cronbach's alpha there, and you see a mean and standard deviation paired together. That is basically all of the descriptive statistics you need to have a fully fleshed out description of what's going on within a single one of your variables. So the discussion that you would want to engage in if you choose this prompt for your weekly discussion post is to think of some variables that interest you and find a PsycInfo article that includes a mean and standard deviation in the descriptive statistics. Likely you'll need to see full text because this information would probably only be in the results section. But once you've got a full paper available to you, check out the results section or the procedure section, materials section. It'll be somewhere there in the middle. Try and find a variable that has a write-up including a mean and standard deviation together, and then just take some notes on what the variables were. Okay, so that would do it for this first unit on descriptive statistics covering visualizations, central tendency statistics, and variability statistics. So I'm going to leave it right there. I hope you guys are doing well, and I'll talk to you soon.